From Iran, and this is my first time actually in Senegal. I arrived last night and I didn't get to see any part of the city, but this morning when I woke up and I saw the scenery, and then I came down and saw the warm welcome of the organizers and the people who are involved in this meeting. I just fell in love with Senegal. So you have a very beautiful city, and I really like it. So my talk is going to be about the principles and application of liquid chromatography mass spectrometry. I'm going to talk a little bit about the challenges that we have in analytical chemistry and the capabilities of mass spectrometry to overcome those challenges. And we're going to talk a little bit about what is called ion monitoring, different methods of ion monitoring. And I'm going to just touch a little bit about the pitfalls of the mass spectrometry and the isotopically labeled compound in mass spectrometry. In analytical chemistry, we have to answer two simple questions. What is in there and how much is in there? Two simple questions, but no simple answers to these questions. And I'm going to talk about the application of liquid chromatography mass spectrometry to answer these two questions. We usually want to identify and quantify compounds in mixtures. That's the challenge. The compounds are together, and they have to be identified and they have to be quantified at the same time. And this brings us to the solution of chromatography. We have to use a simple method or a detailed and an elaborated method to separate compounds. And this is not an easy task. And after we separated them, we have to basically get a signal for we have to get a signal. We have to get a signal which is proportional to the concentration of each one of the samples, and we get a chromatogram. Chromatogram, well, this is not changing there. The chromatogram is a two-dimensional diagram in which you have the time in x-axis and you have the intensity on the y-axis. And this is when you separate the compounds and you get signal separately for each one of them. But if you ask the machine that what are these components, it would not be able to tell you what they are. And we usually use retention time to identify the compounds. But we all know that the retention time is not a very decisive criteria to determine the identity of the compound, especially if you don't know what is in the mixture. And then you don't know the retention time of the compounds, and you don't know what the compounds are you're dealing with. So it's very difficult, and it's practically impossible to identify the compounds. But if you use a detector like mass spectrometry, then the mass spectrometer as the detector would be able to tell you about the identity of the compound. And that's the beauty of mass spectrometry as a detector for a chromatographic system like liquid chromatography. So we have liquid chromatography for separation, and then we have mass spectrometry for identification and quantification both. First of all, I have to tell you that when you want to get a signal out of a mass spectrometer in liquid chromatography, you have to try to ionize the components of the mixture first, and then you pull it into the mass spectrometer, and mass spectrometer give you the mass spectrum of the compounds. So this is how it works. This is this is the what is coming out of the HPLC in the liquid form. And you take the compounds which are coming out of the liquid chromatography and you spray them and you evaporate the solvent out of them, and then you get your compound ionized somehow, and the ions are going to go to the mass spectrometer. And when they go to the mass spectrometer is going to measure them based on their molecular weight and the mass to charge ratio. This would be the chromatogram you get out of a liquid chromatography mass spectrometry. As you see, the chromatogram is just exactly like the chromatogram you have with the classic chromatography and liquid chromatography. But the point is that if you click on any part of these peaks that you get in your chromatogram, you get the mass spectrum of the compound which is coming out. And that is what identifies the compound. And basically, if I want to compare the mass spectrometry liquid chromatography with the classic HPLC, mass spectrometer is going to add a third dimension to the diagram, which is a two-dimensional diagram. And that would be the mass spectrum of each one of the compounds which is coming out of the HPLC system. If I want to give you an example and use an analogy, I would say that what we do in mass spectrometry is what we are doing in archaeology. You know, in archaeology, we dig out the part of an animal like a dinosaur, and then you put them together based on the anatomy of the animal, and then we come up with a structure which is like that. We all accept that this animal existed 1 million years ago, and we never saw them. And that's the beauty of the mass spectrometry. You know, in mass spectrometry, we will not be able to see the molecules, but we do get the information about the structure of the molecule based on the process which is called fragmentation. We take a compound like this, and we try to fragment the compound, and the compound break down. But the compounds do not break down without any rules. I mean, they do fragment according to the chemistry rules, and they do fragment from those parts which are more vulnerable. And if you keep the condition of the fragmentation constant, you always get a certain pattern for the compound. For instance, in this compound, you have a phenyl group, you have an ethylene group, and you have a formyl group. And if you fragment the compound, you get a two-dimensional diagram, which is like that. On the x-axis, you have the mass to charge ratio. Basically, you have the weight of each one of the fragments. And on the y-axis, you have the intensity. And this will be like a fingerprint for your compound. And if you have an unknown compound and it shows you this fingerprint, you would say that this is the same compound that you have in here. So that's what we do in mass spectrometry to identify the compound. So if you have a chromatogram like this and you click on any part of the peaks, it would give you the fingerprint of the compound, and fingerprint could be compared to the library of the compound, and you can identify the compound pretty easy. And that's how we do the identification. But when it comes to quantification, we have to do the same thing that we do in classical liquid chromatography, HPLC UV, for instance. We have to make different standards, and we inject the samples as standards to the machine, and we get signals out of them, and then we do a calibration. We construct a calibration curve, and if you have an unknown, you inject the sample to the machine, and you get a ratio, an area for the peak, and then you extrapolate the ratio or the area to the calibration curve, and you get the concentration out of it. This is the same exact thing that we do in mass spectrometry. But the beauty of liquid chromatography, mass spectrometry, comes out when you realize that nowadays, especially in agricultural science, we do need to analyze one sample with many, many components, and we want to quantify and identify them at the same time in just one run time. Just to give you an example, these are the type of pesticides which could exist in agricultural product. And as the president in the morning mentioned, agricultural products are one of the main sectors of the economy of our countries. And if you want to make sure that the agricultural products are safe, or you want to export them, or you want to give them to the people, you have to make sure that the pesticides are not there at a certain level. So the number, I don't want you to pay attention to the name of the compound, but just pay attention to the number of the pesticide that could exist in one agricultural product. And you are to analyze all of them, and you want to analyze one sample, and you want to analyze all the compounds together in one run time. These are hundreds, like 300 or 400 pesticides together. And you have to analyze them by your technique, and you have to make sure that they don't exist, or if they exist, they are lower than a certain amount. And you see, if you want to analyze the sample once for each one of the analytes, it's practically impossible, and you cannot do that. So we use chromatography to separate them from each other. But let's say you're the best chromatographer of the world, and you want to separate 300 samples in a runtime of 1.5 hours, for instance. This is what you get. All the peaks go together, they co-elute, and you are going to have a nightmare because of that. Because if you want to quantify the compounds, you have to have the area of the peaks, and you have to have the peaks separated from each other. And this is impossible to have like 400 compounds separated from each other in just one run time. So HPLC UV, HPLC fluorescent, any other detectors are out of question. They could not do it. Simply, you cannot separate all the compound in just one chromatogram. But the good thing is that mass spectrometry would be able to separate the compounds even if they are co-eluted and they are coming out of the chromatography together. And that's the beauty of the mass spectrometry when you use it for quantification. How do we do it? If you look at the spectrum of each one of the compounds, for instance, in this example, you would find a fragment which is specifically which exists specifically in the spectrum of this compound, and it does not exist in the other compound. And if you look at the mass spectrum of this compound, you find a peak in, which exists in this spectrum, and it does not exist in the other one. These are called diagnostic ions, diagnostic fragments. So we choose the diagnostic fragment for each compound. And then you would be able to adjust the machine so it can monitor just for that fragment. And that means if you, for instance, monitor just for 93, which is one of the fragments of this compound, and you run the sample again, you get this spectrum. Both compounds are there, but you just get one signal, which belongs to the first compound, and you can do it the other way around, and you just monitor for the second compound. So you make the first compound invisible, and you get the second compound visible. So that means mass spectrometry could separate compounds based on their diagnostic ions. And you can, even if the compounds are coming out of the system together, then you would be able to separate them from each other. This is done by a system which is called tandem mass spectrometry, and it is done by a triple quadruple mass analyzer. What is happening in mass spectrometry and in triple quadruple system is that you have a compound with a molecular weight of 123, for instance. And you fragment this compound. The fragment which forms from this compound is 77. So the transition or the conversion of 123 to 77 is specific for this compound. So you adjust the machine so that it just monitors the transition of 123 to the 77 molecular mass. So if the machine is adjusted with this criteria that I have in here, you would only be able to see those compounds which have 123 as their parent molecule, and they have 77 as their fragments. So this is called an ion transition. And if you adjust the machine on this ion transition, the machine is going to disregard the other compound, and it just sees this compound. And the good thing is that, let me show it in this way. You see, I have 3 compounds in here. They have different molecular mass, parent ions, and when they are fragmented, they are changed to another compound, another fragment, which is different from each other. So this transition, 328 to 272, is specific for the first compound. The second transition is specific for the second compound, and the third transition is specific for the third compound. Let's say these 3 compounds are coming out of the HPLC together. They co-elute. But the machine, the mass spectrometer, is able to monitor all 3 transitions together, and it would give you separate chromatograms that could be measured separately. So even though the compounds are coming together, like these chromatograms that I have in here, you would be able to ask the machine to separate them from each other, and you get a chromatogram like this. So these are the compounds which are co-eluted together. And the chromatograph, the system, the separation system has failed to separate them. But you use the power of mass spectrometry to separate them, and you get signals specifically for each one of the compound, and you can measure the area of the compounds and do the calibration and measure the compound, even though the compounds are coming out of the system together. So this is the highest power of liquid chromatography mass spectrometry in those cases in which you have multiple residues and you have multiple compounds together and the number are outrageous and you want to get signals separate for them, despite the fact that chromatography has failed to separate them from each other. So liquid chromatography together with mass spectrometry would be the best method to identify and quantify compounds based on these facts that I just explained to you, and you would be able to do the multi-residue analysis just in one run time without being worried about coelution of the compounds. This is just a touch of the mass spectrometry. I'm sorry that I don't have so much time to explain more. There is more, and I really would like to wish that I have more time, maybe in other events, to explain to you more about the mass spectrometry and its capabilities. Thank you so much.